Hello, we are Team 5 and I'm going to explain the exercise 5 of the activity 6. In the exercise 5, we must find the general solution of these differential equations. If initial conditions are given, find the particular solution. And we have two different differential equations. We have our first differential equation, and it's a case of Cauchy-Euler equation, and we have two different initial conditions. Now we continue obtaining the auxiliary equation with the proposed formula. We have an m squared plus a minus 1 all multiplied by m plus b equal to 0. Then we substitute the values of a and b, and we have m squared plus 3 minus 1 multiplied by m plus 1 equal to 0. Then we reduce the middle term, and our equation is m squared plus 2m plus 1 equal to 0. And then we can observe that the equation is a perfect square trinomial. We can factorize the auxiliary equation and we can obtain that the value of m is equal to minus 1. With the value of m, we can write the general solution of this differential equation. We have y equal to c1 multiplied by x power to minus 1 plus c2 multiplied by x power to minus 1 multiplied by logarithm of x. Then we must obtain the value of each constant of the general solution. We take the first initial condition, we substitute each x by 1, and the equation is equal to 0, and we can obtain that the first constant is equal to 0. After that, we obtain the derivative of the general solution. We obtain c2 multiplied by minus natural logarithm of x divided by x squared plus 1 divided by x squared, and we reduce a little the derivative. Then we substitute the value of x by 1, and this equation is equal to 4, and we can solve the equation, and the result is the value of c2 is equal to 4. With the value of each constant, we can rewrite the solution and we can find the particular solution. We substitute the value of each constant and we obtain the particular solution is y equal to 4x power to minus 1 multiplied by natural logarithm of x. Now we have the second differential equation, and it's an equation of variation of parameters. We start obtaining the auxiliary equation. We have lambda squared plus lambda minus 2 equal to 0. We can factorize this equation in lambda minus 1 multiplied by lambda plus 2 equal to 0, and in the first case we obtain the value of each lambda 1 equal to 1 and lambda 2 equal to minus 2. With the values we can write the homogeneous solution, and that is equal to C1 multiplied by exponential power to x plus C2 multiplied by exponential power to minus 2x, and we can take the value of y1 and y2. y1 is equal to exponential power to x, and y2 is equal to exponential power to minus 2x. Then we must obtain the value of Wronskian. We will use this value in the next step. We make a matrix. In the first column we put y1 and its derivative, and in the second column we put y2 and its derivative. Then we solve the matrix and we obtain minus 2 exponential power to minus x minus exponential power to minus x. This result is equal to minus 3 exponential power to minus x. After that we must obtain the value of u1 and u2. u1 is obtained by integration of minus y2 rx divided by Wronskian, and the integration is substitute the values of each variable, and we reduce the integration. We obtain the integration of x multiplied by exponential power to 3x. It's integration by parts. We solve the integration in the next slide. And u2 is a similar process. We have a particular formula. We substitute the values of each variable. We reduce the integration, and we obtain minus integration of x multiplied by exponential power to 6x, and we can see that this integration is by parts too. Now I'm going to solve each integration by part, but with a different method. In this method is the abbreviated method to integrate it by parts. This method is used to integrate in situations of we can find the algebraic with exponential expression and algebraic with trigonometric expression. We make two different columns. In the first column we put the algebraic expression, and we derive the first member any times until we obtain a 0, and in the second column we put the exponential or trigonometric expression, and we integrated this member the same times that we derive the first column, and then we multiply crossover first column over the second column, and each time we change the sign. We start with plus, then minus, then plus, and so on. In the first integration by parts, we have x multiplied by exponential power to 3x. We put the x in the first column and exponential power to 3x in the second column. We derive 2 times x to obtain a 0, uh, and we integrate 2 times the exponential, and the same times we derive the x, and then we multiply x uh, multiplied by exponential 3 power to 3x over 3. Then we put a minus, is the second sign, and then we multiply 1 by exponential power to 3x over 9, and we obtain the, or integrate, is x multiplied by exponential power to 3x over 3 minus exponential power to 3x over 9, and we reduce the result, and we obtain exponential power to 3x multiplied by x over 3 minus 1 over 9. Now we solve the second integration by parts. We put the variable x in the first column and the exponential in the second column. We derive 2 times the variable x until we obtain a 0. Then we integrated the exponential 2 times, the same times we derived, and we start with the multiplication. X multiplied by exponential power to 6x over 6. Then we put a minus, and we multiply 1 by exponential power to cx over 36, and the result is the minus, because we have in the beginning of the integration a minus, and then the result x exponential power to 6x over 6 minus exponential 6 power to 6x over 36. We change the signs in the second step, and then we factorize the results, and we obtain exponential power to 6x multiplied by minus x over 6 plus 1 over 36. Now we must find the y particular with the formula yp equal to u1 y1 plus u2 y2. We substitute each value of each variable, and we obtain yp equal to exponential power to 4x multiplied by x over 3 minus 1 over 9 plus exponential power to 4x multiplied by minus x over 6 plus 1 over 36, and we have common members. We can join the factors, and we can simplify the fractions, and we obtain yp equal to exponential power to 4x multiplied by x over 6 minus 1 over 12, and we can factorize this member to eliminate the fractions inside the parentheses, and we obtain finally our yp, that is equal to 1 over 12 uh, exponential power to 4x multiplied by 2x minus 1. Finally, with the values of y homogeneous plus y particular, we obtain the general solution. We join the results and we obtain that the general solution is y equal to c1 multiplied by exponential power to x plus c2 uh, multiplied by exponential power to minus 2x plus 1 over 12 multiplied by exponential power to 4x multiplied by 2x minus 1.